Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So, I am your tutor for the physics subjects. So, in the previous class we will see that the force exerted on the dipole vanishes when the dipole is placed in external fields, because the force on a positive charge and a negative charge is equal and opposites, that is why they cancel. So, today I will calculate the torque exerted on the dipole due to an external field, and we will see that this one is not 0. So, let us first draw a dipole in a uniform field. So, let us say uniform field E, and this one is the x axis, and if we draw a dipole, so this one is minus q, this one is plus q charge, this is I cap, right. So, this one is origin, and the plus q charged, the vector, the distance vector is r plus, we denote it r plus vector from the origin, and the minus q charge place it r minus vector from the origin. So, this one is origin I cap j cap. So, the force exerted on plus q charge in the directions is parallel to the electric field vector, so A plus vector, and the force exerted on the negative charge is the opposite to the electric field, F minus vector. So, in the previous class we will see the A plus vector q times E I cap and F minus vector minus q times A I cap. So, in the direction in the F minus vector in the direction minus I cap, the opposite to the electric field vector, and the net force F net F plus F minus is 0. So, even though the net force vanishes, the field exert a torque on the dipole. So, the torque about the midpoint O, so this is a midpoint of the dipole, torque midpoint O of the dipole is so how to define a torque? R cross F, right. So, in case of positive charge plus q, so the distance vector is r plus cross F plus vector, this is a vector product cross, plus in case of negative charge r minus vector cross F minus vector. So, the r plus vector is basically this distance was, so we consider the total distance is 2a, right, the distance between the plus q and minus q charge. So, the distance from the midpoint to plus q charge is a and this one is a. So, the r plus vector basically a cos theta I cap, a sin theta j cap. So, basically r plus vector, r plus the magnitude and the unit vector. So, now know this magnitude is a times r plus unit vector. So, now we know that how to write the unit vector in terms of I cap and j cap. So, this cos theta I cap and sin theta j cap, and then multiplied by a. Similarly, for other case r minus vector, so a times minus cos theta I cap, so minus a cos theta I cap minus a sin theta j cap. Oh no, there is a f vector also there. So, the cross product of a plus, so this one is a plus the magnitude times I cap plus minus A cos theta I cap minus A sin theta j cap cross minus F minus I cap. So, magnitude is same, but the direction is opposite. Okay. Okay. And by simplifying this, we get A sin theta F plus. Now, I cap cross I cap vanishes, right. So, I cap cross I cap is 0, but I cap cross j cap is k cap, and j cap cross I cap minus k cap. Okay. So, plug into this, so we get that minus k cap plus A sin theta for the other cases. Similarly, again j cap cross I cap, so F minus k cap, right. So, both are same sign, the torque is not vanish. So, the add up, so 2 A f, F plus and F minus, the magnitude is same. Okay. So, 2 A f times sin theta times minus k cap. Okay. Basically, the directions of the torque is the perpendicular to the plane, okay. Perpendicular to the plane downwards, okay, not upwards. Okay. So, basically in these directions the torque minus k cap. Okay. So, in the directions downwards from the plane, okay. And if, so here if, so this one is not 0, okay. So, here f is the same as f plus and f minus, okay. So, both charges feels equal forces, okay, but the direction is different, the direction is into the page, okay. The directions of the torque is into the page or minus k cap. So, the effect of the torque is to rotate the dipole clockwise, so that the dipole moment P becomes aligned with the electric field. So, basically the effect of torque tau is to rotate the dipole clockwise, so that the dipole moment P becomes aligned to the electric field. So, becomes aligned with the electric field. Okay. Okay. The thing is that, so when we place a dipole in an external electric field, okay, so the net force on the dipole is 0, and but the torque is not 0. So, the torque basically rotates the dipoles and ultimately align to the electric field, okay, and that is the properties, okay, of the dipole in an external fields. Okay. So, the dipole is always aligned to the electric field, okay, when you place it in an external electric field. So, the torque basically does the job. Okay. So, the magnitude of the torque can be written as, so the tau, then the 2a times, we know the force value F. So, F is QE, okay, times sin theta. Okay. So, where the theta is, so this one is theta, right. So, this is the angle theta, is sin theta, and in terms of the dipole moment P, so you know that P is 2q A, right. The charge times the distance between the charges, okay, two charges. So, P E sin theta. So, in general expression the torques become, so in general the torque is P vector times E vector. So, this is general expression of the torque when we place a dipole in an external field A, a uniform field A. Okay. So, now we calculate the potential energy of an electric dipole. Okay. So, the potential energy of an dipole when the dipole placed in an external field E, uniform external field E. So, the work done by the electric field to rotate the dipole by an angle theta. Okay. So, first we calculate the work done to rotate the dipole by an angle, let us say d theta. Okay. What is the work done? The corresponding work done is dw is minus tau d theta. So, this is the work done by the electric field to rotate the dipole by an angle theta. Okay. Here the tau is a torque, okay, that we calculated just before, okay. And the negative sign indicates that the torque opposes any increases in theta. Okay. So, if we increase the theta, the torque is opposed to do. Okay. So, theta is the basically if we away from the electric field vector, okay. If we move the dipole away from the electric field vectors. Okay. So, the negative sign indicates so that the torque opposes any increases in theta. In theta. So, the torque is always try to align the dipole moment in the electric field directions. Okay. So, if we increase the theta, then the torque is opposite to that thing. So, and that is why this negative sign here. So, now we calculate the total amount of work done by an electric field. So, total amount of work done by the electric field to rotate the dipole from an angle to rotate the dipole to theta is w theta naught to theta, and torque is minus p sin theta, right, and d theta, right, and we indicate that theta naught to theta what is the work done. Okay. So, this one is P e cos theta minus cos theta naught, right. So, when the cos theta is greater than equals to greater than cos theta naught, okay. So, the w is positive. So, w positive if cos theta greater than cos theta naught, and it is negative if cos theta less than cos theta naught. Okay. So, if you increase the theta, okay, that means the cos theta greater than cos theta naught, because theta naught is your initial angle, okay, and cos theta is the final angle, okay, and the theta is the final angle. So, we increase the theta, that means the cos theta increases. No, I think if you increase the theta, that means the cos theta value actually decreases, okay, and the work done is positive. Okay. So, the change in potential energy, then the change in potential energy delta u, just u minus u naught, okay, and this is one is minus w, okay. So, this is minus p cos theta naught. So, at u naught, so where u naught is minus p cos theta naught, okay. So, this is the potential energy at reference point, and this is the potential energy at final point, okay. So, where the angle is theta, this is the potential energy at the reference point. At reference point, if we choose theta naught is pi by 2, so if we choose theta naught is pi by 2, then u naught becomes 0, okay. We choose the potential energy, the reference potential energy 0, okay. And then the potential energy of a dipole, okay, then u is basically delta u, and this is the minus w. So, minus p cos theta minus p vector dot e vector, okay. So, since that the potential energy is a scalar quantity, so it is dot product of two vectors, okay. So, this is the potential energy of a dipole. So, potential energy of a dipole. Dipole in an external field, okay. So, in the next class we will see that when the dipole placed in a non uniform electric field, okay, and in that case the torque and force both are present, okay, and we will discuss in the next class, okay. Thank you.